Hello. In this video, we'll study the various searching algorithms. Those are beyond the classical search. For example, is a hill climbing search. It is actually a greedy search method. What is a greedy search? Greedy search means the searching process which never gets satisfied till the maximum value is reached, the maximum point is reached. A search process that attains the maxima, the absolute maxima, and before that it never gets stopped, never gets satisfied. There's a greedy search mechanism. Hill climbing is one of them. The hill climbing, as the name suggests, the searching process is just similar to climbing along a hill, means going for better and better objective function value of a certain problem until the absolute maxima is reached, which is called global maxima. That such process will continue to exist. Now, the objective function value. The objective function value can be any value. It may be a linear mathematical function. It may be a polynomial function. It may be exponential or logarithmic function. Any kind of mathematical function can be referred as an objective function. The objective function can be represented by any linear, nonlinear, polynomial, or exponential function. And also there is a concept that's a heuristic function, the heuristic value function. So the heuristic value function typically refers to the distance from the goal. A search process attains the better point, the better node, the better vertex, or the better position in terms of the better heuristic value or the better objective function value. Most of the cases, the objective function value is actually the better objective function value refers to a heuristic value of a function. So hill climbing is actually in mostly it is applied for heuristic functions. So when a search process attains a neighbor, a connected node, a connected neighbor, which is offering a better heuristic value than the current one, then only it will climb up to that particular node. And in this way, the climbing will continue till the global maximum is reached. So this is a hill climbing problem. So we start with the algorithm. The algorithm, before that, we can look at the just a pictorial representation of the hill climbing. So if we are starting from a certain point, suppose from this point where the cursor is um, pointing to, from this point, if we attain the better neighbor in terms of the objective function value, the better neighbor in terms of the heuristic function value, we are climbing along the particular slope of the hill, and at a certain point of time, it can reach global maximum for a simple, straightforward problem. Now, to solving this problem, en route of reaching the global maxima, there can be a number of obstructions or there can be a number of distractions. For example, the shoulder is one of the distraction. There is an illusion of maxima. Global maxima is a local maxima, a flat local maxima, or even an extended flat local maximum, which we can say as plateau. So those are the various situations where the reaching to the global maxima can be obstructed, can be disturbed. No, in case of shoulder, suppose a particular search process, a current node is gradually climbing up along the slope of the hill to the better neighbor. repeatedly and will reach to a point where there is one side, no neighbor is offering a better objective function value or heuristic function value than the current node. And the other hand, and the other side, the neighbors are offering a worse objective function value or the heuristic function value. In that particular case, the search process will have nothing to do other than having some sort of random walk. Random walk. After 2 or 3 step random walk, it can it can get upward rising edge of a neighbor which is offering a better or higher objective function value along the hill. But in case of a shoulder of a hill, if somebody walks along at certain point of time, it can find a upward rising slope. Now, similarly, in case of this local maxima, which is an illusion of global maxima, a node, if it is a current state, it's a current state, it will climb up at this node, then this node, and after that, when it climbs up to the local maxima, it compares all the neighbors and tests whether any of the neighbor is any of the neighbor is offering a better heuristic value or the objective function value than the current one. But here, in this particular local maxima, none of the neighbors are offering a better value than the current because current is in the peak. The local maxima is the maximum, is a peak of uh, a certain hill, the, the hill, the process where it is the local maxima is a point which is offering the better objective function value or the better heuristic function value than the surrounding neighboring points, the surrounding neighbors. But it is not the global maxima. But in the whole landscape, whole problem space, there is some peak which is higher than the local maxima. That is a global maxima. Local maxima is locally the point which is highest locally. Out of all the surrounding neighbors, the point which is offering the highest heuristic function value or objective function value, that is a local maxima. Now, if an agent, search agent, reaches a global maxima, at that point, it can't find any neighbor better than it. So it can have an illusion of being in global maxima, but it is not actually is. Somehow it is informed that it is not the global maxima of a function. It will, there is only one option, main option it is having, that is backtracking. Backtracking along the same path, it can reach to this particular, whenever it reaches to this particular point, it can get a better alternative. It can get better neighbors along this left side, and it can go along the slope of the hill, and one day it can reach the global maxima. This is one. This is a backtracking will be the solution of this local maxima. Now, the flat local maxima. If a agent reaches local maxima and it doesn't, it performs the backtracking, someday it can go to the global maxima. Or if the agent is sticking here, there's a basically the agent is stuck here in the flat local maxima, then it can't go out of this particular trap unless it has a random walk. The random walk towards all directions, and someday it will get a upward rising edge somewhere. So the global maxima. So the random walk and backtracking is the solution of this flat local maxima. Now this flat local maxima, if some agent is walking on the flat local maxima, all over, everywhere, is finding all the neighbors which are providing with the same objective function value. None of the neighbor is providing a better objective function value than the current because all are same. It's a plane, that's why all are having the same objective function value. Thus the search process, the search agent will not be able to choose any better neighbor unless it backtracks and or the random walk to all the directions and it finds the alternate path for rising. Generally, the local maxima, the agent can be stuck in the local maxima, stuck into the local maxima. In normal process, if it chooses the neighbor randomly by random walk, if it chooses a neighbor, then at the next step, it finds the previous previously current node as the better neighbor. Then again it comes back to the current node. Then again it with the random walk, if it comes here, then it again chooses the previously current node as the better one, then again comes back to it. So in this way, repeatedly, the things will go on and it can never go out of this particular trap. Now, only the backtracking and the random walk combination can solve the problem. And for play two, for the extended flat local maxima, only option of coming out of this is the big jump, a random jump, a random jump from the local plate, the flat, extended flat local maxima, that is a play two. From play two, the search engine can have the bigger jump randomly. Okay. In a hope that it may land to a place which is not flat. Okay. It may land to a place where it can get a upward rising edge towards some global maxima or some other points where it can again backtrack or again have a random walk. So these are the obstructions we have of of hill climbing search. Now, if a neighbor is better in any way, the agent will choose that. If a neighbor is better in any way, the current node, the search process will take that particular neighbor and that neighbor will be the current node, become the current node. If it is not that, if none of the neighbor is found to be better, then it will be trapped in these cases, just like these cases. The problem is solved here in case of the algorithm is very simple here. The problem will be solved. The problem will be solved by extended hill climbing. We will discuss that. Before that, the algorithm is function hill climbing returns a state that is a local maximum. Okay. Now, it is returning a local maximum first. Input the problem, local variables, the current node, which is a node, and the neighbor, which is a node. Those are the local variables. The current node and the neighboring node and the adjacent node. The current node will be assigned by the initial state. The initial state, the current node will be the initial node. The initial state or is is actually assigned as a current. The current node will be assigned by the initial state value, and the loop will continue to exist till the local maxima is reached. Neighbor will be assigned by a highest valued successor of current. So which neighbor will be chosen? The current nodes, all the all the connected nodes, all the connected nodes of the current node are tested, are compared among all the neighbors of the current node, among all the adjacent nodes of the current node, is providing the highest objective function value or highest heuristic function value, that neighbor will be chosen as the next one. Now, a neighbor will be assigned by a highest valued successor of current. Suppose a current node is having n number of successors, among which the kth neighbor is having the highest among all n neighbors. So the kth neighbor is chosen as a neighbor, as a valid neighbor. And the neighbor's value will be compared with the value of the current. Which value? The objective function value or the heuristic function value of the neighbor will be compared with the objective function value or the heuristic function value of the current node. If the neighbors is found to be having the heuristic function value, then return the current state. Then returning the current state. The current state will become, it will it will stuck to the current state only. It will not go the neighbor, choose the neighbor. If the neighbor is providing the less value, then there's no use of choosing the neighbor. The search engine will stick at the current node. Otherwise, the neighbor will be chosen and neighbor will become the current node. So this is a very straight and simple algorithm we have. First, a particular current node is initialized by the initial state, and subsequently the current node is updated. The initial state is assigned as a current node. The current node is the initial state at the initial stage. And n number of neighbors, there are n number of neighbors we have of the initial state. And among all n number of neighbors, which is providing the highest heuristic function value or the objective function value is chosen as a valid neighbor. And that neighbor will be compared with the current node. That neighbor will be compared with the current node in terms of their values, in terms of their heuristic function value or objective function value. If the current node is having the value better than the selected neighbor, then we will stick at the current node itself. We will not go anywhere. That is sticking at the current node. And we will stuck into the current node. We will not find any, means the local maxima is reached or some point which is having a value higher than all the surrounding points that is reached. Otherwise, means if the neighbor's value is better than the current, then the search process will jump to the neighbor, the better point, the higher point in terms of the objective function value or the heuristic function value, then neighbor will become the current node. The current node, the current variable is assigned by the value of the neighbor. So in this way, the process will go on till the local maximum is reached. So these are very straight and simple algorithm. So we are having this thing, the local maxima can be reached here. Now, highest among all the local maxima is the global maxima. The highest among all the local maxima is the global maxima. So if an agent is sticked into the local maxima, this is the shortcoming of hill climbing, that it can't be able to reach the global maxima ever if it is stuck into the local maxima. Unless remedial measure is taken in the form of backtracking and random walk or random jump. Now, this problem is solved by an advanced technique called simulated annealing. I'm discussing that. Before that, let's examine some sort of getting unstuck. How to make hill climbing getting unstuck. Pure hill climbing search on 8 queens gets stuck 85.6% of time, 14% success only. 8 queens problem. So it's a very well-known problem of AI. There are 8 queens. The constraint is the none of the queens are having uh, the none of the queens are placed in a same row, neither in same row, nor in same column, or in same diagonal. None of the queens are placed in same row or same column in same diagonal with any other. So this is a 8 queen, 8 number of queens. So what is the optimal state? The max optimal state will that will satisfy this condition. The queens are scattered in any manner. So the optimal state that will have no queens should have placed in same row or same column or same diagonal. This particular position we will achieve. That is the objective we should achieve in 8 queens problem by following the pure hill climbing. 86% time we get success, 40% time we get success. I'm sorry, 86% time we get failure. It is liable to be failed because of this local maxima. We may stuck into the local maxima, the search process. Now the simulated annealing. Metropolis acceptance criteria is a term that is used here. Simulated annealing is a term that is adopted from thermodynamics, where it is stated that a metal is heated at a certain point where the molecules of the metal is become so much will achieve so much kinetic energy that they can move anywhere with a high degree of rapidity. The kinetic energy of the molecules will become the highly dynamic and highly kinetic. Now, in that case, if a metal is heated, the molecules are very, very kinetic, will become very much kinetic, and the dynamic property of molecules will be highest at that time. Now, slowly, slowly, as the metal becomes cooler, the dynamic property of molecules will decrease, will actually decrease. And at a certain point of time, when the temperature decreases to a certain level, the molecules will not move. Explorations of molecules will stop. The movement of molecules will stop and molecules will be stable at certain point. That is the rule of simulated annealing. This principle is used here in computing the greedy to extending the concept of greedy hill climbing. Here the T is a temperature variable. The temperature variable T starts from a higher point and slowly, slowly decreases. And as it goes on decreases, as it as it decreases, the rate of exploration of the vertices decrease. And at a certain point of time, the vertices will stop exploring, and it gets settled to a point, and that is the end of the process. Okay. Till that time, the temperature variable T gets to its minima, okay, reaches its minima, the process will go on. So you see here, the input is a problem, okay. I'm mapping from time to temperature, okay. Local variables current, next current node, next node, T, a temperature controlling probability of downward steps. I'm just coming to that, the probability concept here that is used to solve the problem of hill climbing and the stacking of any search agent in the local maximum. The current is assigned by the initial state. Here, as usual, the current node it starts with the initial state, and the T starts with 1 to infinity. The T is a temperature variable. There's a loop counter here. That is 1 to infinity, it will go. T, the new T will be the schedule of, there is a temperature schedule that is alpha, that is a fraction by which the temperature decreases. So new temperature equal to is the schedule of T that defines how the temperature decreases. New T equal to alpha into old T. Alpha is a fraction, is a discount factor. Alpha is a discount factor. So new temperature equal to alpha into old temperature. So that is temperature schedule. Having the temperature parameter is assigned to the current temperature. If the temperature is zero, then return the current node. Whatever, if temperature becomes zero, just like a metal, if the temperature of metal becomes zero, all the molecule was stopped to move. All the molecules will stop, will settle to a current point, current position, will never move forward, will never be moving any further step. So in that case, if T equal to zero, we are returning the current wherever it is. The next will be assigned by, otherwise, if T is not zero, till the T becomes zero, T starts with 1. T starts with a variable value. So T means small t is a loop variable, capital T is a temperature. And schedule of small t, it is a function of small t, step is a function of the step. We are having the step, uh, t is 1, t is 2, t is 3, whatever, is a function of small t. The capital T is initialized with, and it decreases with that. It decreases. It's a decrementing function of t. As t increases, small t increases, the capital T will decrease. This is one of the mechanisms of controlling the temperature variable T, capital T. The small t is a index, loop index number, is a loop counter that 1 to infinity, and capital T, the temperature variable, is a decreasing function of small t, schedule of t. As small t goes higher, the capital T goes lower. It is geometrically goes lower. Now, Another mechanism of temperature, handling the temperature variable is T equal to alpha into old temperature. Alpha is a fraction. Sometimes the alpha can be 1 by number of iterations plus 1. Alpha can be 1 by alpha equal to 1 by number of iterations plus 1. So there are various mechanisms to represent the decrementation of temperature. Okay. So when temperature becomes zero, absolutely decreased to the lowest level, then it will return the current node wherever it is, the current state. Otherwise, the next will be a randomly selected successor of current. Otherwise, the current is having the, if temperature is not zero, still the current, still the search process can go. Still the molecules are having the kinetic property. Still the molecules are having the dynamic property. Still the molecules can move. So still the starch process will go, can proceed. So explorations to the new neighbor is not stopped till the capital T becomes zero. So the next will be a randomly selected successor of current. Successor means a neighbor, descendant neighbor, successor, the neighbor. Okay, randomly selected neighbor, okay, will be chosen as the next, not the highest. Randomly selected neighbor will chosen as the next node. Now, delta E. Delta E is a difference variable, means objective function value of the next, which is randomly chosen neighbor of the current. The objective function value of the next neighbor or the heuristic function value of the next neighbor minus the objective or heuristic function value of the current node. So the difference between the values of the next node and the current node is referred as del E. Now, if del E is positive, means if the value of the next is offering a better value, the next neighbor is offering the better value than the current node, then definitely the current node will become the next. Next will become the current. So the search engine will jump to the next because next is providing the better value because del E greater than zero. Del E greater than zero means the value of the next neighbor is better than the value of the current one, current node. Otherwise, if it is not providing the better, in hill climbing, we used to be stuck in local maxima, but here it is not. Here we are saying, even if the neighbor, randomly selected neighbor, is not providing a better heuristic function value than the current, we will not discount the neighbor. Neither we will cancel the neighbor or dismiss the neighbor from being selected. We will select that neighbor by a probability. What is the probability? E to the power minus del E divided by capital T. E to the power is the exponential function. E to the power del E minus del E. Del E means the difference between delta E means difference between the value of the next and the current. If the next value is lower, not higher than the current, if the next chosen neighbor is not providing the higher value than the current, then also it will be chosen by some probability. And the probability is e to the power minus delta E by T. E to the power minus delta E by T. So, in that case, what will happen? All the neighbors, in this way, the neighbor is chosen by that probability. This means, suppose e to the power minus del E by T, some point of time, a neighbor is having the e to the power minus del E by T. Del E means the value difference between the neighbor and the current. And T means, capital T means temperature at that point of time. So e to the power minus del E by T, that probability, suppose, is 0.5. This means it is chosen by the probability 0.5. The interpretation of this is for every 2 steps, for every 2 trials, that neighbor will be chosen once. For every 100 trials, that neighbor will be chosen 50 times. So for every 2 trials, the neighbor will be chosen at least once. At least exactly once. For every 10 trials, the neighbor will be chosen 5 times. So the rate of acceptance of neighbor is established by this probability. The rate of acceptance of the neighbor is established by this probability. Actually, there is a random walk. I think not exactly random walk, and there will be a probability given. So 10 number of walks if is made, then 5 number of times that neighbor will be chosen. Or every 2 walks, one time that neighbor will be chosen. Or if the search engine have 2 walks, then in first walk, in the first or second walk, one time that particular neighbor will be chosen. In this way, it distributes probability to all the neighbors. The probability distribution is made to all the neighbors, and none of the neighbors are rejected. Even if the neighbor is not providing a better objective function value, none of the neighbors are rejected, but all the neighbors are selected by probabilities. The probability is distributed. This means the probability is represented as a degree of acceptance of certain neighbor. This doesn't mean that neighbor is partially accepted. This means the interpretation of these for certain amount of trials, for certain amount of steps, that particular fraction of time, that neighbor will be accepted. Suppose if the probability of certain neighbor, okay, by the metropolis acceptance criteria, the probability of certain neighbor becomes zero point 0.4. This means for every 10 steps, 4 times the neighbor will be chosen. In every 5 steps, okay, 2 times the neighbor will be chosen. So this is the way. Okay, for every 2 steps, maximum 1 step, the neighbor will be chosen. So this is the the rate of acceptance. Okay, the comparative weightage of acceptance is determined by distributing the probability. All the neighbors are distributed by specific probability, different probabilities. And that is e to the power del e by t minus del e by t. That means where del e is the value of the next minus value of the current. Value of the next minus value of the current. If del e is negative means value of the current is higher than the value of the neighbor. Value of the current is higher than the value of neighbor. So in that case, e to the power del e. So for each neighbor, this particular daily varies, changes. And then T means at that point of time, what is the temperature? That determines the rate of explorations. If temperature is high, it is it will walk very much frequently. There's a tendency of selecting neighbor. There is tendency of jumping to a better neighbor will be much higher. When the temperature goes low, the tendency of exploration goes lower. And at a certain point of time, the exploration stops. So this is a simulated annealing by which the stacking into the local maxima is absolutely prevented. And there is no question of being stuck in a local maxima or in the plateau or in a flat local maxima or in the shoulder. There is no question because the nodes are selected according to the probability. If it is not better, then also it will be chosen by the probability. By that, it is seen by using the simulated annealing, one point of time and much, much lesser amount of time is taken also to reach to a global maximum. So the algorithm is complete. The algorithm leads to the optimal solution. Surely, and the algorithm is complete also. So we have this reality of the simulated annealing. Thank you so much.